everyone, and welcome to my talk. I am Wenxiang Qian, and today I am going to talk about my recent research on GPU virtualization, named Another Road Leads to the Host from a Message to VM Escape on Nvidia's vGPU. And first, a little introduce on myself. I am now doing security research in many fields, including virtualization, web browser, IoT, and well, as you can see, I almost change my research directions every year to learn from different fields. And I am now interested in and also studying further developing and machine learning. And here, introduced to my team. I am now working in Tencent Blade team, and which is funded by Tencent Security Platform Department, and we have researchers in many fields like AIoT, mobile devices, and cloud virtualization. And now I also listed our homepage here. Here's the agenda of my talk today. First, I will introduce the backgrounds of my research and then the structures of their installers. And following the most important part, the vRPC message and its handling. In the end, I will sum up some security best practices and my advices on using vGPU. Here we go. Let's start from introducing the GPU virtualization. GPU virtualization technique allows users to share a GPU card in their own VMs. It is used in various applications such as desktop virtualization, cloud gaming, and computational science. It is generally involve one or more techniques such as device emulation, API remoting, fixed pass-through, and mediated pass-through. In fixed pass-through, a GPU is accessed directly by a single virtual machine exclusively and permanently. This achieves almost native performance. In mediated device pass-through, the hypervisor sends graphical commands from guests directly to the GPU. This is a form of hardware-assisted virtualization and achieves near-nature performance. And as you can see, Nvidia, AMD, Intel, they all support the vGPU. Now let's move to the specific product, the Nvidia vGPU. And it can be used in a data center, allowed GPUs to be shared across multiple virtual machines. And according to Nvidia, many famous cloud service providers are providing vGPU service. And some are in pass-through mode, some are using full vGPU functionalities. The vGPU is restricted to certain data center and high-end cards like Tesla and Kujo. And after you have registered an Nvidia Enterprise account, you can download the installer from its application hub. And you should choose suitable installer for your environment. Our test environment is a server with a Tesla T4, and the operating system is CentOS 8. After you downloaded the installers, you can find two different installers with extension .run. The vGPU kvm.run should be installed in the host machine, and grid.run should be installed in the guest machine. After it's installed, they will have a Nvidia.ko in both guest machine and host machine. The installer can be extracted again, and you can find some open source files in both installers. It's same as other Nvidia graphical drivers. The Nvidia.ko has some open source files, but critical code logics are closed source. And you can search for .o binary files for its closed source part. And other components such as Nvidia vGPU Manager and live Nvidia vGPU.so, which is also called as the vGPU plugin. They are both closed size. And the daemon Nvidia vGPU Manager will run in the background in the host, and it will spawn itself when a guest is starting. The guest must use GPU in mediated device pass-through mode. The right center figure shows the loop. vGPU Manager will fork itself when there's a guest is started. The vGPU plugin is loaded by Nvidia vGPU Manager, and the plugin plays the main role, which is responsible with communicating with the guest. The guest uses a mechanism called vRPC to send requests within the hypervisor and processed by the lib Nvidia vGPU.so. And as you can see, the main logic stays in the plugin. So here we will take a close look at the plugin. The vGPU plugin receives and processes vGPU requests. Whenever there are some new data in the RAM buffer, it will take the data out and check if it's a legal vRPC message. The vRPC message is limited to a maximum 4 kilobytes, and the vRPC message can be very frequently sent. So it is using a global area to store the vRPC message. If the vRPC message is legal, it will call the handler for vRPC message. And the function names are all obfuscated and shows in 6-digit numbers between NV and vGPU. And you can find the log string vGPU message signature mismatch to locate the caller of the message handler function. And here we have a simplified model. And honestly, you don't need to focus on most part of this picture. All we need to know is Nvidia.ko in the guest sends the vRPC message. The vRPC message is processed by the plugin in the daemon process Nvidia vGPU Manager, and the Nvidia vGPU Manager will communicate with the Nvidia.ko on the host, and all of this is enough. Here's also a table listed the structure of a vRPC message. The vRPC message is consisted with a 32 bytes header, and the rest is the message body. You can treat the message as an array of little ending unsigned integer. Normally, you will only care about the packet size and vRPC command number sections in the header. First, let's put the vRPC message sender aside. I will introduce it later. After receiving the message, the vGPU manager running on host machine will try to check whether the message is legal. Because vGPU manager uses messages in this way on both Windows and Linux, and some messages are system specific, it will block some wrong messages at this step. The wrong messages is such as some unsupported message sent by the Windows client from the guest to the Linux host. And after the check is over, it will call the corresponding handler according to the message number. If any error occurs in the handler, an error reporting function will generate an error message. If no error occurs, it will copy the vRPC message body, which is stored in the host before, and back to the guest machine. And during the message processing, the content of vRPC message body stored in the host may change. And do you remember the error handling we have mentioned earlier? And it will generate different error messages for for each RPC message before the function returns. And this is an interesting step. You can see there's also a big switch case in the error handler. So as a security researcher, we may also want to test this function. Until the mystery of this function is discovered, the meaning of the vRPC messages has never been known by myself. So after carefully analyzing its code, we were surprised to find a lot of information. This error handling function saves the meaning of each message and each field. In this way, we can more easily find from the message name, which the RPC message name, which operations look more dangerous and more likely to have vulnerabilities. For example, the top center figure shows OX17 RPC message is named RPC alloc event, and we know it is allocating something. And it has three members: H client for body offset 0, H object for body index 1, and notify index for body index 2. And in addition to get a lot of information from this function, we are also very interested in the switch case that come with it. From the perspective of developers, because the complexity of switch case, even if the company has a code review, experts may not be able to review all the details of all branches. So after we have marked the pseudocode generated by Ada. We copied it into the IDE and made a father. So in short, our father skips the message processing part, but directly calls the error handling function. The input sample of father is the vRPC message generated by father engine. So we use father to check whether the error handling function can handle various errors correctly. And father did find a zigzag V, but this problem has been fixed in a newer version. But anyway, it brings a lot of convenience for the follow-up and analysis in this obfuscated binary. And here I have listed 6 important vRPC messages. They will be introduced later. As you can see, there are many messages except H client and H device. These 2 handles are very important among the calls. Although they are called handles, the values are not as random as you might think. On the contrary, we can specify almost any integer as a handle. So let's start from reading the RPC message handler. We have mentioned how to locate its outer function earlier, so here's another string you can use to locate in the middle of the handler. You can see here also many checks to ensure that the handler and the message is correct. And some lines below the check, you can see there's a big switch case. The variable it is switching case is vGPU message, which is a message number from the vRPC header. You can see the function table is a big array, stores the pointers to different handlers. The easiest way to get the function table is, of course, set a breakpoint here and grab them all. The handlers are fixed, and so once you calculated all the handlers, you are okay to do the further static analysis for each handler. The second argument to the handler is a vRPC message buffer. Let's remember this information and start to find our box. So we already know how messages are stored in the host, and now how do we send a vRPC message from the guest? Since the detail of how the guest will send a message are not what we care about in our earlier stage of reverse engineering, in order to avoid the complexity, we decided to patch Nvidia.ko of the guest machine. And this means we will reuse its code but with a patched value to send a custom vRPC message. But how to find a function that is sending a message? We already know that the vRPC message consists of a signature vRPC in its header, plus other fields by analyzing the Nvidia manager on the host machine. But if you search for string vRPC in the guest driver, you may not get any useful information. However, if we search for integer CPRV, which is a little ending byte order, we can locate a function whose content matches our known information very well. By checking its reference, we can confirm that this function is initializing a vRPC message header. And the second parameter is used to control the RPC message number. The third parameter is used to indicate the required size. As you can see, this size will be added with header size, which is 32 bytes to fill in the message. So remember, don't set it too close to 4 kilobytes, the size section. So that is to prevent the message from failing the Nvidia manager's check. And interestingly, we found that there are 2 functions that always appear in pairs. So based on intuition, we can also guess that the second function is used to send a vRPC message. The picture on the right shows the renamed functions. The code in between 2 functions is obviously filling the vRPC body with specific values. And here, A2 plus 608 plus 32 represents data field of vRPC body with index 0, and 36 means data field of body index 1, and so on. After sending the message, send the vRPC message will wait for the host to return the result. So after doing that, we can also use this code logic to obtain its return value. The reading of the return value is the same as we are writing the vRPC message body. So you can just read the data from the A3 plus 608 plus offset. The question is, which function should we choose to patch? To find the answer, we set a breakpoint on the vRPC initialization function, and then we found a function called NV00777RM, which is very lucky number, and it will be called every time the guest driver is loaded. And however, it should be noted that while Nvidia is updating the driver, the standards obfuscated name may change. From our observation, this number may become larger in the newer versions. So when we wrote this slide, it has already gone increased to 779. And on the other side, there's also a file named nvidia.ko in the host kernel, which confuses us at first. And fortunately, we quickly figured out its relationship with the nvidia.ko in the guest machine. And in addition, because part of its code is open source, so it can also help us understand an important process easier, which is the meaning of parameters when it's entering RM/IO control. If you have audited Nvidia vGPU Manager, you may find that almost every I/O control sent by vGPU Manager will get into RM/IO control. So this also explains why RM/IO control is not open sourced by Nvidia, because it is strongly related with the vGPU logic. According to the code comments, we can also know that RM stands for Resource Manager. The figure on the right is a function that you will often see when auditing the vGPU plugin. I named it, according to its log, as nvrm control, which is the main entry point for sending RM/IO control from host user space. The data used to send is usually a structure allocated on the stack. Its last three parameters are usually command, data, and size. And you can use the IOC size or IOC NR macro to parse them, as here shown in the bottom left, to get their original definitions. However, the size used in the manager may be different from actual definition, so it's just for your references only. And next, when we try to exploit some vulnerabilities, so we are also very surprised to find that its main program did not enable the ASLR. I guess it is because that it needs to be compatible with the old logic in some drivers. At the same time, it is not protected by stack canary too. So therefore, except for the address of .so libraries it loads, which have a certain degree of randomnesses, but the vGPU Manager itself does not enable the ASLR. So this makes it easier to exploit those vulnerabilities. And let's take a look at its startup process. The main program runs in the form of a daemon, and the child process is spawned by the main process through fork when the hypervisor is started. So every time the child process starts, the memory layout of child process is the same as main process, and the crash of child process will not affect the main process at all. If the hypervisor process restarts, the child process will also restart. And although Nvidia vGPU Manager is multi-threaded, if we use a guest in the simplest text mode, it will behave like a single-threaded process. That is because the text mode guest sends almost no requests to the vGPU plugin. So no matter how many times the client's vGPU Manager is restarted, its memory layout will almost stay the same every time, which also provides convenience for us to make multiple attempts. And although the main process does not have ASLR, the main process also has only a few functions. Therefore, we still need to pay attention to the more feature-rich and more concentrated vGPU plugin. By the plugin, it is address randomized, so we also need to find a way to bypass the ASLR. The vulnerability of information disclosure will be our first choice, but it is obvious that the amount of reverse engineering is too much for us. And at this point, my analysis has been going for some time, and I have marked almost 70% of key functions of the vGPU plugin in Ada, and centered on the message handler function. Therefore, it is better to directly generate .c files through Ada, pretending to audit an open source software. We first tried to use static code analysis tool to do this work, but the result was not very good. So let's rethink about it. If we want to get the leaked data, we need it to put the leaked value in a vRPC message and then return to the guest. This writing process requires it to operate on a keyword operation. Because the address of a 64-bit program is equivalent to a keyword, so I tried to search the code where the vRPC body is on the left side of the assign mark, which is the equal mark, and they're operating on keyword or keyword asterisk or void asterisk. And soon we located 3 places, but only this one in the figure below meets our requirement. And let's take a look here in detail. This code belongs to message 0x35 RPC update PDE2. And at the top, if the vRPC body data we passed in has a value, it will write the address of its own local variable into the corresponding position of vRPC message body. Then, if it passes NVARM control successfully, that is, IO control does not return an error, the message handler will return successfully afterwards. And this stack pointer will remain in the vRPC body and return to the guest. This is a perfect information leak because assuming that the client's vGPU manager is like a single thread, it means that the stack pointer it returns here will always have same offset relatively to the start of the stack area. But we have some trouble when we are debugging it. The IO control fails every time, and this structure is as big as 16.4 bytes data. Obviously, brute forcing it is unreasonable. So we used the GDB script to fuzzy it, and finally we made it return successfully. And compared to brute forcing of 16.4 bytes, it's better to use a little randomization during the fuzzing. And through the messages OX2 and OX20, we can create 2 handles. The value is manually specified by us. We know that these 2 handles is often used by message handlers. So after we created these 2 handles, we wrote a huge loop in the GDB script. The loop will randomly set the value of each field from a set of fixed values, such as 0, 1, OX100, and OX7 FFFFs, like this, and including those 2 handle values. And the loop modifies the value of some of the variables randomly. If there's no findings after a period of time, the variables are randomized again. We use a fixed pseudo-random number generator, so it can be easily reproduced if we run into any problems. And we finally passed the check. In addition to ASLR, we also need some memory corruption to complete the entire exploit chain. When I was auditing the handler, I found several very large functions, each of which has many thousand lines of code. I've always liked to audit those super large functions. Super large functions always means super big complexity. The code may be good and safe in the first, but after a period of time, the code will change more or less. And maybe it's to improve code efficiency or add some features. The problem of large code blocks is then exposed. Even with code reviews, unit tests is still very difficult for technical experts or software engineers to analyze the subtle changes in the code to each branch of this huge function. And the message name of OX1A is DMA control. DMA has always been a hotspot for security researchers. This is an operation that crosses the boundary between the software and hardware. It is definitely an important logic to analysis, even in other software such as QEMU. And here is DMA plus RPC. This is as conspicuous as a warning sign on the side of the road. There are 2 very long callback functions which are used for data initialization and finalization before and after DMA. There is very long if-then and send IO control expression in the middle of this handler. You can easily spot it. It's sending the IO control that executes the DMA request. This handler will call DMA control get param size with the DMA number, then memory alloc to allocate a buffer for DMA. Size vary from different DMA numbers. It should be mentioned that IDA may have bugs when generating the pseudocode for this function. The return value will look smaller than correct value in the ADA. So I recommend you to refer to the assembly code to get the real allocation size. I named the initialization function as first half processor. It will fill the data according to the DMA command. And we have found 2 vulnerabilities in this function. Let's take a look in the first half processor. When the DMA commands we send are OXC637, O1, or O2. I will call them O1 and O2 for short. The function logic in the first half processor seems a bit wrong, especially O2. O2's while loop is equivalent to the memory copy. Also, the O1's is also very similar to the memory copy, but it will skip some bytes. And you can see neither of these 2 cases limited how many bytes to copy, because in the pseudocode, Ada didn't put 02 into switch case, but instead using a goto to jump to its handler, so we didn't saw 02 at our first glance. And so our exploit will use the branch of C6370101. The branch of 01 will copy data with holes. Please look at this code. In the bottom left figure, it will copy data to the DMA buffer with index 9 multiplies I and then plus 3 to 10. For example, when I is equal to 0, the buff's index 3 to 10 will be filled with values. In the next iteration, when I equals 1, buff's index 12 to 19 will be filled with values. In other words, every time it copies 24 bytes, it will skip 4 bytes. I will call those 4 bytes as holes later. And since it is a heap overflow, we should be interested in the data after the overflowed heap. After a few hundred bytes, we found an interesting heap trunk. The content seems to be a structure with several points stored in it. Let's attach the vGPU manager, set an access breakpoint on this memory trunk, and then resume the program. As soon as vRPC returned, the access breakpoint was triggered. We found that the caller is a function located in the main program, but not a vGPU plugin, as shown in the figure below. This function is comparing an address to the value stored in this memory trunk. The memory trunk where we set the breakpoint is a node in a linked list. The code is testing whether the pointer is the same as the first item in the linked list. If they are the same, it will remove the item from the linked list. After some attempts, we found that in the picture on the right, if v16 is set to 0, then you can pass subroutine 404BEO and then enter the function set item value. I named this function, but the name is somewhat ambitious. From the perspective of the attacker, this function is setting the value of a certain memory block. And from the developer's point of view, this function is used to remove nodes from the linked list. Let's take a close look at the code logic. And this function, you can see such a textbook-like chain removal operation. And as you know, the work of removing the chain will inevitably modify the prev and next value of nodes before and after it. Does this operation remind you of the unlink operation of malloc in the older version of libc? We will also use this opportunity to set the previous and next values in vulnerability exploitation. Okay, let's read the code again. The variable p is the memory trunk overflowed by us, so its value is totally controllable. And moreover, this function will call mmap or munmap according to the value of memory trunk p after finishing the linked list operation. So we can set p prev to mmap.got minus the offset of next field relative to the beginning of the structure. Then set p next to the address of our first rope gadget. When we write p next to p prev next, the got of mmap will be overwritten with the address of the first rope gadget. But there's a problem here. You can see it will also set p next prev to p prev. P next is now the address of the first rope gadget, p next prev is just a few bytes behind the rope gadget. This means if we want to exploit it in this way, we also need the memory trunk of first rope gadget to be writable. Of course, it's also to be executable. But the RWX memory is rarely seen now, so here it leaves us a big question mark. And to my surprise, the program have many RWX pages, and they are all used as a stack. This means that we can put shellcode on the stack and then use the stack address as the first rope gadget's address. The first thing came into my mind was some functions like main, they are called earlier, and their stack frames will remain in the program and almost don't change. Therefore, I dumped the stack memory and searched for the rope gadgets. There are some gadgets, but I did not find any rope gadgets that met my needs. So now there's only one way, that is, I need to find a way to put the rope gadget on the stack manually. One target is find a function, and that function will use a very super and unusually large amount of stack space, and it will modify the memory area that is located very deep in the stack. When that function exits, the stack memory it applies for will rarely have a chance to be reused by other functions, so my gadget can live in the stack in this way. Now I only need to search for the .c file exported by Ada. I used a regular expression to search who is using a lot of stack memory. I've got some candidates, and after I compared function among them, I'm sure that the processor of the message OX3C will be my choice. It takes up about 14.7 kilobytes of stack memory. Please check the snapshot in the top. And also the function is quite simple. After entering it, it will copy the value from vRPC message body index 6 to stack variable v55, and v55 is located at RSP plus OX B888. Then it is used to send an IO control. If error happens in the IO control, it will report an error and exit directly. This can be a primitive for placing shellcode on the stack. It only does the necessary operations and then exits, with minimal influence to the overall memory layout. Now we have this primitive to put a gadget on the stack, so how do we combine this with unlink process? First, we write a 4-byte rope gadget to the stack, and thanks to the fork, you can treat it as a single threaded program waiting for external input to do the task. Therefore, as long as the order of each vRPC message is not changed, the relative offset of the rope gadget to the beginning of the stack memory is also unchanged. And furthermore, all objects' relative offset that we will use later in our exploit chain won't change either. So now we can finish the last step, which is assign p prev to p next prev. The rope gadget we used is move RSP RSI then return. The figure in the right top explains the reason why I choose to set the RSI. The RBX in the figure is is pointing to the memory trunk P. So RSI is got from controllable memory area. The length parameter of mmap has type of size t, which is always the same length of a pointer. So we can move a pointer into this RSI register from p plus 8. The pointer points to our fake stack, which are the memory trunks before variable p. And don't forget, we already set the mmap to this rope gadget 1. So when mmap is called, actually, our rope gadget will run. So we can complete the stack pivot through our rope gadget. So everything now looks fine, but because C637011 will have holes when copying the data, the stack will also carry 4 bytes of zeros in many places. But this can be avoided by choosing rope gadgets carefully. Now let's deal with these holes. Regarding these memory holes, we can use those holes cleverly when we adjust the memory layout. For example, we can treat them as the number 0 or use 4 bytes as a higher 32 bits of address. The main manager process is loaded on address 4 with 5 zeros, but this is a 64-bit program, so using the 4 bytes of zeros as part of memory address is feasible. Also, we can choose a suitable rope gadget to either pop it out or skip it. Adjusting memory layout with those holes is a very time-consuming step in the debugging, so it needs some patience. And after I figured out the memory layout and wrote the whole POC, now we need to patch guest kernel driver to send messages. I manually patched a large area in the guest driver in advance, so basically all we need to do now is to split the bytecode of the POC into many assemblies to write data into vRPC message buffer. The RAX in the figure represents the start address of the vRPC buffer. As you can see, this is very painful. I have made a program to help me to do the most of work. And it can help me to calculate the offset, the value, and the bytecodes, and generate a patched guest nvidia.ko file. When the patched guest driver is prepared, now it's time to trigger the vulnerability. I have found two different styles of hypervisors during the test. One is that the hypervisor does not exit when the clients restart, the system restarts. And type 2 is when the client restarts, the hypervisor also exits. Because the vGPU manager will also exit when the hypervisor process exits, therefore I have listed two methods for triggering the vulnerability. The method 2 does not require you to reboot the guest machine. You can choose one of them according to your environment. They are equivalent. To myself, I prefer to use the method 1 because it takes less steps. And finally, we can trigger this vulnerability from the guest and run arbitrary program in the host machine with root privilege. The overall success rate is about 40% to 50%. That's because sometimes the stack address can move forward or afterward a little bit when vGPU plugin is loaded. But you can restart your guest machine as many times as you want in a cloud environment, so I think that doesn't matter. Because time is limited, so instead of a long video here, I only put a snapshot which is showing the moment of a calculator is popped up in our host machine. And in the end is some security practice in using vGPU. And most important thing is update your software regularly. And because the Nvidia vGPU manager is running in root, so maybe you can use your firewall to restrict what it can do, or use a host intrusion prevention system to monitor the process activities. Also, administrator should monitor strange crashes on the host machine and report them to Nvidia when you think it is a dangerous crash. And when there's 0-day and some hotfix patches, which you can also call them as workarounds, they could also be applied. For example, you can loop some vulnerable message handlers or functions that are not frequently used. And here are some CVEs that are involved in this talk. And some vulnerabilities are scheduled to, some other vulnerabilities are scheduled to be fixed in the end of July. And this talk is recorded earlier, so they are not listed here. And due to the responsible vulnerability disclosure program, so we have removed some contents from this slide. The deleted contents does not affect the completeness of the speech. So please follow the official security bulletin and updating your product in time if you think your products are affected. And that's all. And thank you very much for your listening. Thank you.